In this video, we're going to describe a procedure for modeling grade beams that are supporting upper level columns or slabs or walls, and the grade beams are being supported by pile caps and piles. So we're going to show two different approaches to this and some of the pitfalls that belong to both approaches. We're first going to go ahead and open the program in Edge, and we're going to use Floor Pro. So we're going to model essentially pile caps as an elevated set of slabs with columns representing the piles. And in the second scenario, we're going to shift over to Adapt Mat and use a actual beam element for the grade beam. In this first approach, we're going to use walls as the grade beam. So let's go ahead and open Builder 2019. We're working here at the current plane. If I turn to a side view, you can see we're working at this first elevated plane. Going back to the plan view, I'm just going to model some slabs here. So we'll model, this really is just a pile cap. So we'll model a cap. We'll make this cap, let's say 24 inches thick. And we're going to go now to column, and I'm going to model a circular column, 12-inch diameter column, and we'll say that these are piles. So this is, again, just representative. I don't have these spaced appropriately as you would have maybe in a pile schedule, but this will do the job for us here. Now what we're going to do is just copy that over. So I'll copy that over to here, and we're going to add a wall. So I'm going to model a wall. Now everything is being modeled below the reference plane. So if I go back to the side view, we can see everything is modeled below that. And I can make different elevations or different heights for these stories. Right now everything is set to 10 feet. We'll go ahead now and model a wall. So this is really what we call, maybe consider a grade beam that's carrying multiple levels above it. And I'm going to now take this and just copy this over, let's say to here. Okay, and I'll go and back to a 3D view. I want to make sure that these walls are actually above this level. So these need to be from the current plane to the top plane. I'll select them, modify, and I'm going to move them to the top plane, like so. Now when the program auto restrains these walls, because they're not actually covered entirely by slab, it's only going to add a line support at the top. So if I go to model and say create supports, we can see that there's a rotationally fixed support here, but the translation is released. Okay, so that will work for us in what we're trying to accomplish here. I'll turn off the line support. At this point, I'm going to go up one level, and we're going to just put a slab on this level. So I'll just add a slab. Maybe we have some loading on that slab. We'll go to loading. Under patch load, I'll go ahead and just add a live load. We'll say there's 100 pounds per square foot on this slab. And I'll go into the story manager now. From model, we can go to story manager, and I'm going to add additional planes. I'm going to add 3 more planes above this plane. So we'll take all of this and copy it vertically 3 times. We'll go over here to modify vertical. We're going to copy this up 3 times. Okay, and now what we have, if we go to multi-level mode, you can see we have something that looks like this. Let's go back to our default display. These slabs are a little too thick. Those are set to 24 inches. We'll modify the selection on those slabs, and we're going to make those slabs just 8 inches thick. And if we go to a rendered view, this is what our system kind of looks like. Now the goal here would be potentially to design these walls as beams, which is not really doable with how the program uses design sections over components. So analytically we can obtain a solution here, but if I go and replace these with beams, which is what I'll show you, we have a stability problem because the beam gets referenced off of the plane that it belongs to. In this case, it's going to belong to either this plane here. Let me just draw this in here. It will either have to be referenced from this plane or referenced from the bottom plane with an offset upward. So that creates an issue. So again, analytically, this works. We can see overall behavior. We can get reactions in the piles, actions in the pile caps, but we can't really design that grade beam, for example, assuming that these lower walls are actually grade beams that are full story. So let's go back now. I'm going to go ahead and save this. Okay, and we're going to go to analysis. I'm going to mesh this system. We're working still in multi-level mode, so we'll mesh this. And now we're going to analyze. And again, my objective is to make sure that the system is stable, that we have connectivity between components, and also to view the forces, let's say, in the piles, and also to determine perhaps reinforcement in the cap based on those forces. So one thing we'll do is we'll just make this a taller floor where we have the piles. We'll go to current plane, and I'm actually going to make that 40 feet. Okay, so now we have something that looks like that. Okay, and let's go back now, and I'm going to now analyze this. I'll just analyze this for the default combinations. We have a couple of serviceability combos and then strength combos. So we'll go ahead and analyze globally. That's completed. And if we go to the results viewer, we're going to just take a look at the global deformation for the structure. So we'll go over here to Z translation or to global. We'll do global 3D, and we can see kind of the behavior of this, how we've currently modeled this. So we have something that looks like this. You can see this kind of inward bending here. This is fixed to the wall, so we get this S shape curvature here on this wall stack at the lower level. And you can also see some vertical deflection in that wall, or in this case grade beam. If we amplify this, you can see that a little clearly, more clear. So here we just get severe deflection in those slabs. But that's fine. This is just for investigation's sake. So once that's done, we can now use these results mainly to determine capacity, whether or not we have axial forces in these piles that might exceed their bearing capacity, or also the bearing plus potentially skin friction for the pile, and also just actions in the pile caps based on the way that this is built. If we go back out of here and into the main view, let's go ahead and go to single level mode. I'm going to navigate down to this level, and I can just switch this to columns only. And under, for example, under service total load, we're going to select column, and we can go down here to axial force. So now we have a view of the axial forces in those piles, and we can see the piles near the connection with that grade beam are getting axially loaded much more so than these exterior piles. This just shows me the distribution of those forces in the pile groups. Okay, so that's how we can obtain the axial forces. We could also produce a report and go to, for example, column reactions to pull out those pile reactions. Secondly, if we turn that off and we go back and turn back on our pile caps, I may want to determine bending and shear in the pile cap. So we could develop a series of strips. So I might add a strip along here. We might space that strip every 2 feet or some set spacing we want to define. I'll just take the strip and I'll modify it, and we're going to modify it by coordinates. We'll say we want every 2 feet, and we're going to do 5 of these cuts. And we would also potentially put these in the Y direction also. But now I can go and generate design cuts and design those cuts on the pile cap. This would then allow me to view actions on the cuts. So if we go to, for example, strength, over here in the load cases that we're looking at and we want to view results for, we can come back on design sections and check bending, shear, etc. So let's scale this down. And if I go to 1, 2, 3, just to see all the values here, we can control the display of the section cuts that we're looking at. So we have bending moments, shears, and so on. We could also check punching shear for these columns that are below the cap. So there's several different things we can do from a design perspective. The one thing we cannot do, however, is actually design this grade beam because it's modeled as a wall. If I change that grade beam or if I change that to actually a beam component, then we have potential issues. So if we convert this rather than modeling this as a wall, okay, and a wall is connected at two different planes because we mesh vertically in the wall. We have a top and bottom reference plane. If I was to go in and model a beam along that path, okay, we'll go to model. Let's just put a beam along the side of this. If I model a beam along this path, you can see that beam can be shifted vertically. I can create an offset for the beam, so I could create a depth of the beam that's quite tall. It's 120 inches in this case, and then I could create an offset, but that beam still is only connected to one level. There's only one level that's referenced from, so it cannot connect between two levels in order to transfer load through the beam to the level below, and that is problematic in trying to set up a model like this. So if we want the ability to design not only the piles, the pile caps, and the grade beams, we have to take a different approach. And so what we'll do is model something similar, but in this case, we're going to use adapt mat. Thank you. So we've reopened the program with adapt edge and mat in place, and we'll notice here that the actual pile caps that we've modeled in this model are located at the bottom plane. If I look at a side view of this, we can see we have a bottom plane, a current plane. If I go to multi-level mode, we have several planes above that. Now there's one distinct difference here in that in this case, if I want to model these as grade beams, the distance between this level here is 20 feet, so 240 inches. This is a 10-foot deep grade beam, and then we have columns that are actually modeled from current plane to bottom plane, but then we offset them back up by 120 inches. In this type of a setup, the program requires the use of columns to be stacked on these beams. So if you needed to simulate, for example, the load transfer through more points other than just these three, then we might have to put in a series of columns to represent better distribution of force down into the beam versus just some discrete points where we have the columns modeled. We have the beam here. Let's go and take a look at that beam. And this beam is modeled as 18 by 120, and you'll notice the location, I've offset it by 120 above the bottom plane. It's actually extended slightly into the pile cap. It could be extended further. You'll notice once we mesh this, we're going to have to do some manual manipulation of the mesh. And then we also have loads just like the other model. So this isn't identical to the other model, but it's similar in nature into how this is set up. If I show the loads here, let's look at the patch loads. These are the loads on the structure. So what we're going to do now, let me turn those loads back off, is we're going to analyze this and analyze it globally. We first need to mesh this. So let's clear out the mesh for the full structure. And we want to show one more thing. If we go to Model Visibility Panel and we turn on the point springs, in this case, what we've represented in terms of piles are springs. These are just point springs. If I double click on the spring, we have a vertical subgrade modulus assigned. These are compression only springs. And so this is representative of how we would model in an adapt mat versus actually modeling a physical element that represents the piles. We do this with springs. And the next step we're going to take here is we're going to mesh the structure. So I'm going to mesh this at 2 feet in this case. And if we try to analyze this, go back and execute the analysis, you'll notice that there's this option here whether we substitute compression springs with fixed supports, which allows us to superimpose load case results to form the combination results, or we can analyze using compression springs, which takes a little bit longer. We have to obtain a solution for each independent combination. If we go ahead and use that compression spring option, you'll notice the program circles several locations where we have straddling of shell element nodes over the beams. So if I go back to that bottom plane in single level mode, you can see that these elements don't follow the analytical reference line for that beam. If I turn that on under visibility view settings, beam symbol, you'll notice this is our reference line for the beam. We have to mesh along that line and have some connectivity between that line where we have nodes of frame elements and also the shells. And so what I can do here is I'll just select my shell elements and I can manually manipulate them. I'll just move them, for example, down to that center line. And then here, we may actually move that point out to that point there. And these are, again, just manual modifications to the mesh at this level, making sure we have proper connectivity of those elements. So this one I'm actually going to move down to this point. We have something going on there. This is kind of an elongated element there. We may want to mesh this at a tighter spacing. Let's go back and mesh this level at 1 foot. I'll turn off node shifting for this level. Okay, we still get straddling here, so we'll come back and this gives us a little better distribution of elements over the slabs and, or in this case, the pile caps. I'll move this point there to the beam end point. And over here, goes over to the beam center line. Same thing on this last beam. So we're moving to center line and also to endpoint of beam on that last set of nodes. Once I've done that manual modification, I'll go back to the main model globally and we're going to execute the analysis. We don't need to redo the meshing, we just did that and then we made the manual modifications. And this model runs fine. We'll go to the analysis results again. And here, if we go back to global translation and look at the 3D view, we get something like this. And we can see the bending in those beams. I'll go ahead and increase that. We can also look, for example, at the beam diagram. So if I go to a wireframe for that beam, and we can turn on these frame diagrams. Here, these are the global displacements for the beam. If we go to beam actions only, I can check vertical shears, moments, etc. in those members. So those can now be designed because they're modeled as beams versus the first model we modeled those as walls. So going down to the base level now, we could do the same thing. We could set up strips inside of these caps. The point springs, those reactions are now given under the reports analysis reactions. So they're not a component necessarily where we can look at axial forces. We can produce this result where we can print out the reactions for those springs. And then finally, if we wanted to design the actual beams themselves, we can now generate strips along that beam path. We already have a support line there. Let me go ahead and remove this one. I just need to display the other one. So I'll go ahead and generate the sections. You see we have 2 support lines. I'll design those cuts. And again, if we wanted to review results for those cuts, they're shown here at the reference plane, but they apply to this beam. If we double click on any of the cuts, we can see the physical section. The depth here is 120. And now we can generate, for example, actions for those cuts. So looking at the bending action, shear, and so on. This then allows us to directly design the grade beam. If you have any questions about this process, please let us know. You can contact us at support@adaptsoft.com. Thank you.